Now we just taken examples for finding the deflection at point B due to this UDL load, and we found that deflection is WL to the power 4 on 8EI. Now I like to demonstrate one experiment to see that how the relations with the moment of inertia and delta B. Now let's take a demonstration. For example, let's say this is the support A and support B. Now in that case, I take this paper beam. So assume that this is just a simple A4 papers, printer papers, and I use as a beam. Now let's say this beam is subjected to a load. Now this beam is subjected to a load. So when I apply the load, this beam is just have a very large deflections. Now I use the same paper, same materials, and I just fold it in that fashion. You can see this, I just the same A4 papers, and I just fold it, and I make the beam for this folding papers. And if I use the same loading, you can see that this beam has very small deflection. It does not have much deflection. What is the reason behind it? The reason is this one, that if you take this simple paper, the moment of inertia I is very small, and if you take this geometry and moment of inertia for this folded paper has a very large moment of inertia. So that's the reason here that this moment of inertia is inversely proportional to the deflection. So when you have very large moment of inertia, your deflection is very small. That's so on by using this folded paper, which has a very large moment of inertia compared to these plain papers, which has very small moment of inertia. Now this moment of inertia is what? So if you take the centroidal axis, the material that distributes it from that axis is very small. When you are taking the center axis for this folded paper, so the center axis, let's say for example, do you have the center axis, and the material distributed from that axis is more when you comparing this simple sheet. So this moment of inertia is explaining that the materials are distributed far from that central axis would give you the larger moment of inertia. Thank you very much.